This is the Section 5.1 Mathcast. It contains 3 lessons. Students conceptualize probability density functions from relative frequency histograms, then use histogram areas to find probabilities associated with random variables. The uniform distribution is introduced as the student's first true probability density function. Then normal probability density functions are introduced and used to model familiar situations. The concepts presented in Lesson 5.1.1 are largely a review of Lesson 1.3.1, where relative frequency histograms and ogives were used to find percentiles and probabilities. Random variables are defined, returning from Lesson 1.3.3 where they were first introduced. The charity race event scenario is introduced and is used to extend the concept of finding probabilities from histograms to relative frequency histograms and summing histogram bar heights to summing the area of the bars, making them behave like a probability density function. It's important to note that this transition is only possible because the bin width for the hat size and race time histograms is equal to 1 unit. If you're interested in making more examples to solidify the concept of relative frequency histogram areas translating to probabilities, make sure that your histogram bin widths are equal to 1 no matter what situation you're modeling. Students should be familiar with probability notation for probability problems and answers, since their use in Chapter 3. This lesson begins the formal understanding of random variables in probability notation. And this curriculum as a whole requires probability notation and appropriate random variable notation as part of showing work for every probability calculation. In Lesson 5.1.2, using uniform probability density functions, students reason probabilities from values of random variables and reason values of random variables from probabilities. Because students live in a world of manufactured items that have the illusion of sameness, they may be learning for the first time with some conceptual difficulty that exact values of a continuous random variable have a probability of 0. It might be helpful to explain to them that manufactured items are made to fit tolerances because exact values are not possible. The time model in problem 5.11 can help in an intuitive way, because it's easy to believe that no model can predict a future earthquake to an exact moment. The model shows this because the areas in a probability density function represent probabilities, and an exact value of a random variable would represent an exact time as a line, and a line has no area. It is unlikely that the students will encounter a uniform probability distribution on the AP exam. However, the uniform density functions are important here to building on the idea that probabilities can be found through areas. The idea that probability is equal to area and not always delivered from a mysterious calculator function is central to the course. The uniform probability density function problems are included in the problem generator to enforce this central concept. The students must reason with simple rectangular areas to find probabilities, as most calculators do not have a uniform CDF function built in. In Lesson 5.1.3, students now fit a normal curve to the charity race time and hat sizes from Lesson 5.1.1. Standard deviation is tied to the normal probability density function via the empirical rule and used in problem 5.20. Some students may be uncomfortable using a theoretical model that stretches to infinity in both directions, beyond any possible values of the physical situation. In a problem like this, you would need to watch for students putting a 0 here, because a negative time certainly is not possible. Issues like this are real-world considerations when applying a theoretical model to physical outcomes, but you can tell your students, for simplicity, in this class, when using a theoretical model, we will accept all of its ideal representations. Because of the ready availability of calculators that can return values for all normal probability density functions, in this curriculum, calculating z-scores and then using the standard normal distribution is not required for all normal calculations. The standard normal distribution is introduced in Lesson 5.2.2, and its use is required for certain types of problems. See 5, 37, 38, and 39. Use of normal probability density functions continues in Section 5.2, including the inverse normal functions and the standard normal distribution.